Guys, welcome back. We have another review problem here for the upcoming chapter 11 and 12 exam. And in this problem, we have a 12-pound model of the Earth here at C that is rotating around these points. There's a cable from A to C, cable from B to C, and it is rotating. And when the cables are taut, it is 3 feet from the center. There's a 40-degree angle between the vertical and AC and a 15-degree angle between the vertical and BC. And we are given that both wires are to remain taut and that the maximum tension for any wire is 26. So this gives us a range, right? For remaining taut means that at the low end, B here will be 0, and at the maximum, at the other end, then AC will be 26, and we'll see. I think intuitively we can recognize that AC is going to be greater than BC, but we'll see that in the analysis. We are asked to find the range of values for V. So the velocity when it's in motion, it is moving in this direction, which is irrelevant, doesn't matter as long as it's moving. Right, and I have taken the time just to write down the sines and cosines to save time in the video. So let's get to work on this. So this solution. So as always, we start with a free body diagram, and we're into motion now. So free body diagram equals kinetic diagram. And here, note that the motion is along the horizontal. So what I'm going to do is I'm going to put here, I'm going to do my best to say this is the this would be what? This is the acceleration in the tangential direction. This is, and I guess this would be mass, right? This would be mass in the normal direction, which we can think of as also the negative x. And I guess the brackets around that because this is an actual value, this is your direction. And then I'm just going to add in this is not part of it, but this would be the y direction. Right, so just to give us a reference, we have two different frames here, and the normal and tangential are entirely in the horizontal frame, and then I have x and y. And the way to think about this is that the normal and tangential with the y is the equivalent of cylindrical frame. So these are the kinetics on the forces. What do we have? We have the weight. And then we have the tension of AC, and let's just call it tension B. Yeah, so tension B and tension A. And if we put in the horizontals, or excuse me, the vertical here, and I guess we could make that a dotted line for visibility. Then this is 40 degrees, and this is 15 degrees. Okay, so now we are asked to find this range, and so what we need to compare at the end of this, and the parameters of interest here are the velocities, right? We want the range of velocities, and we want the tensions, right? This is, we have a given range of tensions. So we're going to end up looking at the normal acceleration because it gives us velocity that allows us to bring velocity into this framework. So let's start with let's do a sum of the forces in the, let's say the y direction. Why not? So sum of the forces in the y. Now there's no motion in the y direction, right? Because it's circling around this. So the sum of the forces here is going to be 0. And what are these forces? So T a cosine of 40. The cosine of 40 is, let's just write it down. Cosine of 40 minus cosine of 15 and minus W. Right? So we can substitute the cosine 40, cosine 15 with these values. So what do we get? We get 0.66, excuse me, 0.766 TA. And we can just say equals W. We know W is 12. Plus 0.966 times TB, right? And this tells us that TA is always going to be greater than TB. Okay, and that's where we got those values. So we can actually start to think about that. So if TA is always going to be greater than and CB is always going to be less than, then at the point where the wires are just barely taut, right? So at the minimum value, then TB is going to go to 0, right? So what can we say? We can say, let's make a table over here. So at the minimum, we'll say at V min, then TB equals 0. So we'll just put this over here. We'll say TB equals 0. And what does that give us for TA? That gives us, well, that's 12 divided by 0.766. So TA equals, and I'm just going to do this on the calculator. So I'll say 12 divided by 0.766. Right. So, okay, and that is 15.666. That'd be pounds, right? We're in pounds. Okay, so at V max, TA equals 26 pounds. So what is VB? Or excuse me, not VB, TB. Oh, all right. So if TA is 26 pounds, then TB, let's solve this for TB. So TB equals 1 over this, right? So 1 over 0.966 times. So what we got to do? We need to subtract 12 from this side. So 0.766 times 26 minus 12. Okay. So when we do that calculation, we have let's see, 7.766 times 26 minus 12 is that divided by 0.966 gives us 8.195. Here, E equals 8.195. Okay, all right, so now we have the tensions at each range, which is good. So now let's do a sum of the forces at the normal, in the normal direction, and that allows us to bring V in. So the sum of the forces in the normal direction is equal to man, M-A-N, and that is that. So let's substitute our values in. So we have in the normal direction. Well, normal direction is here, so these are sines. So TA times the sine of 40 degrees is 0.643. I'll just go ahead and do that. 0.643 TA plus the sine, TB times the sine of 15, 0.259 times TB. W is vertical, motion is horizontal, so there is no W component, but that is equal to the mass times this, and mass here we're given the weight, so it is the weight over gravity, and that would be times V squared over rho, squared over rho. I'm just going to keep going with this. W is 12. That is over 32.2 times V squared, which we're solving for. Rho is 3. Now be careful with that, by the way. The axis of rotation is about this. It doesn't have anything to do with the wire. So the radius of curvature is 3 feet. So 3 feet. And by the way, we need to make sure that these are dimensionally consistent, right? So I know that they are because this is feet per second squared, this is feet, and this is pounds. So it'll work out, but just make sure that it does. So when I multiply this together, if I just keep going one more, then I get V squared, and that is times 12 divided by 32.2 times 3. And that gives me 0.124. So if I rearrange this, then I've got this and this. So V squared equals this inverted, right? So 1 over, I'm going to divide this, is going to become 1 over 0.124. So I'll just do that. So if I send that to the -1, then it's 8.05. So what I get is V equals the square root of 8.05 times this, right? So 0.643 times tension A plus 0.259 times the tension in B, right? And now I have an equation, and I can just feed these values into here to get both, right? So let's see, if I do the max values, let's see, V, well, let's go with V min. That equals the root of 8.05 times TB is going to be 0. So this is 0. So it's just 15.666 times 0.643. 1212, okay. And then equals, just from the calculator. Wait. 643. All right, and here I get Vman equals 9 point, and that's 0.005. So I'm just going to go with 9.0 meters per second. Likewise, Vmax here. Same thing, 8.05 times, what we got now? We got 26, 0.643 plus 0.259 times 15.666. Wait, Vmax 8.95. One more here. And Vmax is, let's see, this one is 5 and 12 point, that says 315, so I have to say 12.3 meters per second. So the big deal here, the takeaway, is to recognize when to head off and find these values with relation to each other, right? So often when you're asked to find a range of values, what you need to do is consider the endpoints, which is what we did with this sum of the forces in the Y. And once you have that, once you have a table of values, and the key is if you can make a table of values, generally you should. And by virtue of making that table, then later on when we need the values, then we have them. Because if you just consider what would happen if we were stuck here, then we have 3 unknowns, right? So we can't solve it. So then we would have to head back and try to find some pathway to get these values. And so with that, that is how you do that kind of problem. And I will see you in the next video.